So let us start now with the differential calculus, and this is another very important chapter. And so the title is Differential Calculus, the introduction. And of course, the differential calculus is not only important in mathematics, but in all applications. First of all, physics, in particular kinematics, when you study kinematics, and you know that the position of a point particle is represented by a vector. The vector position, which traditionally is r of t. Here there is the origin of your reference frame. Here there is the mass m, the point mass, which is moving along a curve. And by the way, in many books you find that a point particle is something which is small, and this is completely idiotic to be said, because small with respect to what? A very large object can be a point particle in the modelization of the Newtonian mechanics. So what we ask to that is that the motion is just a translation. Okay, if your object translates, then you must know just the position of one point of the object, and then you reconstruct all the objects. So this is, by the way, when you will read very soon that a point particle is something that has to be small, you are allowed to laugh loudly. So this is the position vector. And you know that the velocity is the derivative of the position. And the acceleration is the derivative of the velocity, and so on. Then also in the study of economy, the inflation is the derivative of price. So in a sort of average between different objects to be bought. And there are many other examples, and for instance now we are talking about epidemiology. And one says something that the increasing rate of death has diminished. This means that RT is decreasing, but this means that the number of deaths is not decreasing, is still increasing, but more slowly than before. And this is when you hear or you read in the newspapers some statements like that, so the rate is increasing and decreasing. From now on, you can understand it in terms of differential calculus, and then you will understand that the true meaning is really more subtle. But I want to give you another example, an example which is quite different, and that comes from tides. So tides are a very interesting chapter of physics, of mechanics, and tides have been studied for centuries because they are really the link between the two worlds. The worlds of the earth, what is beneath the sky, what is under the sun and under the moon. Under the sun Of course, you think of this beautiful song by Pink Floyd, Eclipse. Everything under the sun is in tune, but the sun is eclipsed by the moon. Okay, we will talk about the sun and the moon here. And so, because tides happen on Earth, so the sea and the ocean grows and then decreases, but this is connected with the presence of the moon and of the sun. And this has been interpreted as a sort of signal of the sky, of God on the earth. So it is really a connection, and so it has fascinated many scientists. And the history of the theory of tides is extremely rich and extremely fascinating to be studied. So I think now it is also in English, but there is a very beautiful book by an Italian scientist and historian of ancient science whose name is Lucio Russo. And his book in Italian is Flussi e Riflussi. A very nice book. And he talks about the theory of tides, and then he discovers what is the first, so to say, better than correct scientific theory of tides, because in general there is no correct physical theory. There are scientific and non-scientific theories. And the first scientific theory is very ancient. You will not imagine when it was formulated. However, what is the mechanism of tides? The mechanism is the following here. Consider the Earth. Sorry. Today it is difficult to consider the Earth. So this is the Earth. Okay. And suppose this is a very simplified model due to Archimedes. So suppose that the Earth is uniformly surrounded by water. So the oceans are here. So when there is no tide, this is the situation, this is water, the oceans. But now, here, there is the moon, because it is just the moon and not the sun. But, okay, this is the moon. And when the moon is there, the waters that surround the Earth distribute in a different way. Something like that. I am a bit exaggerating it. This is what happens. So what happens here is that the water in this part, so the nearest part to the moon, is attracted by the moon. So it presents a bulk. So people here see the high tide here. The same happens for the part of the water which is farthest from the moon. Okay? It takes the shape of a bulk. There is another bulk here. There are two bumps here and here. And also people here sees the high tide, even though the moon is exactly at the antipodes. It is in the farthest possible position. Okay? So I don't want to go deep into this argument, but whereas this part of the tides is quite easy to explain because moon is there and moon attracts water, it is a bit more technical to understand why also this part determines a high tide. because you would expect perhaps that this part is attracted towards the Earth because it is attracted toward the Moon. But this is not the case. Why? The reason is quite simple. The reason is that the Earth too is attracted by the Moon. But this part is attracted not so strongly, but a bit less, because it is farther. And this part is attracted more. So, what here is important is not exactly the intensity of the force in the various points, but the differences between this intensity, the difference between the intensity of the force here, here, and here. This is what determines the tides. Okay? So, now try to perform a computation about that. So, first of all, we use some symbols in order to do these computations. So the distance between the Moon and the Earth will be capital R. So R is equal to the distance Earth, Moon. Then we have other important elements in this computation. So small r here is the radius of the Earth. And then I recall you the Newtonian formula for the gravitational force. F of d is equal to a certain constant c divided by 2 square. Now it is not important what is the constant here. And this is the intensity of the gravitational force between two masses at a distance d. Okay? And now we compute the force in these 3 points. Point that I call A, which is here. So a point that I called B, and the center of the Earth. Okay? Now, so first we have F at a distance capital R minus small r, which is the force exerted by the Moon at the point A. Then F of R is equal to the force exerted by the Moon at the point C, the center of the Earth. And at the end, F of capital R plus small r, which is the force exerted by the Moon at the point B. Okay? And now what we see is what is the difference. As I told you before, what is important is the difference of the force. What is the difference between the force in A and the force in C. So F capital R minus small r, force in A, minus capital force in R is equal to C, and then 1 over capital R minus small r to the square minus 1 over capital R to the second power. And so this is just a matter of elementary algebra. So here I gather R squared divided by capital R minus small r to the second power, and then I have the difference between the two squares to compute. So R squared minus capital R minus small r squared. And what I find at the end is that this is equal to C. Here we have the double product 2 times small r capital R minus small r to the second power, and here capital R to the fourth power minus 2 r to the cube, r plus... No, I don't want to do that. Plus r squared. This is equal to C. And here we first write here so here we gather this strange term. What I'm doing here, I'm taking the first term here, a numerator, and then at the denominator, instead of putting all this guy, I put here r to the 4, and I neglect the other part. I neglect this part because there is a small r, and small r, the radius of the Earth, is somewhat smaller than capital R. So I think it is negligible, but of course I want to present you exact computation. So if I add this term here, then I will subtract here. So I just put here plus 2 small r capital R minus r to the square, and here r to the fourth power, so the original denominator, 2 r to the cube r plus r squared minus the term I added at the beginning of the bracket, 2r r divided by r4. So notice that here what I find is that this is equal to C, and then the first term, I simplify one term r here, so it is 2 small r divided by capital R to the cube, and the rest is Lie the law of R as R goes to 0. Why? Indeed, if I mark in red these two terms and I compute them here, at the numerator we have 2 small r to the fifth power minus r squared capital R 4 minus 2 r capital R to the fifth power plus 4 r squared capital R to the fourth minus 2 r cube capital R to the fourth is equal to Lie the law of R as R goes to 0. Why the law of R? Because these two cancel, and all the rest shows a power which is at least 2 in R. So it is Lie the law of R. And so this is the important result of this computation. So we learn a very interesting fact here from the point of view of my modelization. The first is that the tidal force, and here let me say, goes like, is proportional to, this is proportional or equivalent. We say it goes like 1 over r cube. So with the inverse of the cube of the distance between Moon and Earth, instead of 1 over r squared. Okay? This is the answer to something puzzling, because if you collect the data on tides, then you find that tidal forces are somewhat weaker than gravitational forces. So you say it is not possible because tidal is gravitational. Why there is 1 over r cube and not 1 over r squared? And the point is exactly that tidal force does not depend on the absolute force on the Earth, but rather on the difference between the forces here and here, or also here and here. Second, this is a physical statement. Second, it is a mathematical statement. Now, consider this expression. We have f, what we found at the end. Capital R minus R minus F capital R, so the difference between the forces, is equal to some C, which here plays no role, over capital R to the cube times R plus lead law of R as R goes to 0, is very similar to what we wrote in the fundamental theorem of integral calculus. Capital F of x minus f of x bar is equal to another function f x bar, x minus x bar, plus lead law x minus x bar, as x goes to x bar. And so what we have here is, let us try this formula now. Here, starting from here, this is the difference between the forces in 2 points, and here we have the increment in F. And here we have that this increment is proportional to the increment in the independent variable x, and here we have a higher order infinitesimal in the increment of x. Okay? And this is exactly the decomposition that we have in mind, and that will give us the definition, the correct definition of the derivative. The increment of the function we are studying is equal to the sum of 2 terms. The first term is proportional to the increment in x, and the second is a higher order infinitesimal. So going back to tides, and So you can be a bit puzzled by the appearance of this C here. I wanted to put this C here in order to talk about forces. You are more familiar with forces, but probably it should have been more correct to talk about acceleration. If you think of acceleration, then you really have no worries about this C, because it is clear that the gravitational acceleration is the same on every mass, regardless of the fact that some masses are larger than other masses. So if you are really not at your ease with this C, so just don't think of forces, but rather think of accelerations. This is the first point. And other point, and as an exercise, okay, repeat this computation. Repeat this computation for point B. But what I want to stress here is that from a physical important phenomenon, we got to a computation that has the same structure of what we found here. Even though the problem was not to compute an area, the problem was somewhat the other way around. Starting from the knowledge of capital F, find small f. Capital F is the gravitational force, and small f is the tidal force. Okay, I don't want to make it longer, but now we start with the derivative, and this here will be the definition of derivative that we will use. So let's go to the next video.